Welcome to a new unit on electric circuits. In our previous unit on electrostatics, in general, the charges that we looked at were sitting still. That's why they're called electrostatics. Now, there were a few questions where we got a charge moving, looked at change in energy and how fast something was going to be going, but pretty much we were just dealing with one individual charge in that case. In this new unit, on electric circuits, we're going to focus very much on charge flow, on lots and lots and lots of charges moving and how this affects different things. So this first lesson, lesson 1, is called Ohm's Law, and we're going to look at some research that was done by a guy with the last name of Ohm. Surprise, surprise, a lot of these laws in this unit are named after the people who discovered them. And the first thing we're going to start out is taking another look at voltage. So we looked at voltage before already in the context of electrostatics. And to start out, we're going to fill in what we already know. So it says fill in the following key fact about voltage. Well, what is the definition of voltage? Remember that it came from looking at actually electric potential energy. And we said that voltage was the energy per unit charge. And as an equation, we had EP over Q. So the amount of energy per charge that we have. And so energy measured in joules and charge measured in coulombs, and we called this 1 volt. A joule per coulomb was a volt. Another word for voltage was potential or electric potential. So although this was important in our last unit, we're basically just going to leave this name behind us and focus on voltage for this unit on electric circuits. So we know that voltage or potential is measured in volts and it's a scalar. We know that EP is our potential energy measured in joules, and our Q was our test charge measured in coulombs. That was our equation for voltage from the last unit. So what's going on inside a voltage source? In this case, we're going to take a look at a battery. A battery has both a negative end and a positive end. So essentially what's happening inside the battery, and this is done by chemicals, is that work is done by separating charges. Whoops. In other words, at the beginning, all the positive and negative charges are mixed throughout, and then work is done to bring all the negative charges around to the negative side of our battery, and work is done to bring all our positive charges, in this case, usually positive ions, to the other side of our battery. So we want to separate positive and negative charges. Remember that normally they would attract each other, so it takes work to separate them. And by doing that, we're going to see that it has several effects when we start connecting up the ends using wires. The circuit symbol for a voltage source looks like this. So instead of actually drawing the battery every time, we draw a short line followed by a long line, and each short line and long line represents a separate cell. A cell is what we would usually refer to as a battery. In the sense of a circuit, a battery is all the cells put together. Then again, the negative is going to stand, the little side stands for the negative side of my battery, and the long end is going to be the positive side of my battery. So you're going to see a lot of the time in your circuit diagrams this symbol. And if you just have one cell, you can have just one short line, one long line, and it just keeps going. So again, short line negative, long line positive, and these would connect up to wires on either side. So to help us understand what's happening in electric circuits, it's helpful to have a mechanical analogy. In other words, an analogy that you can feel and touch and kind of experience for yourself. Now here in Bolivia, you may not have ski hills, so we might have to think through a better analogy that would apply better to Bolivia. But hopefully you've been to a place of the mountain, or you can kind of imagine what this would be like. So the analogy that we use here is the ski hill analogy. Recall that in the previous chapter we said that the gravitational analogy of voltage, when we were thinking about voltage in the beginning, we said, well, voltage is potential energy over charge. And in terms of gravity, it was the analogy of voltage is height. So EP is over mass times gravity. So if we're looking at our circuit, we have a power supply that gives us voltage. Say we have a 6-volt battery or a 6-volt cell. So all our electrons, or the current that leaves this circuit, goes through the resistor. So the cell gives it energy, and when it goes through the resistor, it loses the energy. It loses the 6 volts of potential and then continues on till it gets back to the cell. So we've got a complete circuit. We gain energy from any power supply, a battery or a cell, and we lose energy in any kind of resistor. Similar idea when we're looking at the ski hill analogy. When you go up the ski lift, we are gaining energy. Maybe we're gaining 6 meters of height, and that gives us potential energy. Then we go along, and as we go down the hill, we're going to lose those 6 meters of height and lose the potential energy that goes along with it. So we go up the hill, along the top, and we come back down again, and then we probably ski back to the bottom of the ski lift in order to go up the hill again. So voltage is like gaining a height in terms of your circuit, and then a resistor is like going down a hill to lose that quote-unquote height. So the voltage at a point in the circuit is like the height at a certain point on the mountain. The voltage gain in the cell is like the height a skier gains on the chairlift. The voltage drop in the resistor is like the height lost as the skier moves down a ski run. So the potential, or voltage, is like height. Positive charges want to fall downhill in the same way that a ball wants to roll downhill. The potential energy due to gravity, which is mgh, is like the potential energy due to electricity, which is Q delta V. The only reason the V doesn't have a constant like the G in front of it is due to how we define the volt. So mgh is equivalent to Q delta V. We're going to use this analogy over and over and over again. So again, take a minute, think it through, make sure you're understanding it well before we move on to the next section.